Lecture 20, Solutions. This is actually the last lecture in the series. So yeah, we're at that point of the semester, believe it or not. So let's first talk about solutions involving gases. And here we're going to apply a law known as Henry's law. As you may remember from much earlier lectures, we talked about the idea that having a mixture, a homogeneous mixture where you only see one phase, is what we've been depicting as a solution. And solutions of this kind can be thought of your traditional liquid solvent plus, solid solutes that you mix together, you form your homogeneous solution. And also, you may remember that the solute is the substance present in the smallest amount of moles, to be most exact. Right, like in the case of salt, the salt itself, the sodium and the chloride will be the solute present in the least amount of moles. And then the solvent is the substance present in the greatest amount. Here I'm exaggerating it by, writing up a lot more water molecules around it, but it is present in the greatest amount of moles. Now, a solution may not need necessarily to start with a solid solute. You could actually have a liquid solute or a gas solute. And in the case of the gases, there is something very interesting that we need to talk about. Now, for gases, the ones that we're going to kind of be looking into right here, gases that don't necessarily react further with water, usually they tend to be non-polar gases, although some of them may have some polarity associated with them. But like carbon dioxide, dioxygen, dinitrogen, and argon, these are non-polar gases. And water being a polar substance, highly polar substance, in fact, um, we might say, well, we don't expect these gases to dissolve to a great extent in water, and you'll be correct in saying that. But there is a certain amount of these gases that actually gets to dissolve in water. And if you look at it from the point of view of dioxin, it's kind of a prerequisite that you do dissolve dioxin in water. Otherwise, aquatic life wouldn't be able to breathe, wouldn't be able to survive. Something cool is that because we're looking at gases, we can look at some of the properties of gases in regards to solubility. Specifically, we could look at the partial pressure of the gas present and see how that affects the concentration of it in solution. And for pressures that are relatively, moderate uh, to low, what we do see is that there is a linear correlation between the solution concentration and the partial pressure of the gas. The more pressure of gas you have present, the more of that gas that gets to dissolve in solution. And that kind of goes hand in hand with Dalton's law of partial pressures, meaning that with higher partial pressures, in reality, what we're saying is that we have a greater number of moles of the gas. So it kind of does make sense that you will have more moles of gas in solution as a result of increasing the pressure. And this is in essence what we call Henry's law. And it's a rather simplistic equation. Simply put, what it says is that yes, increase the number of gases, increase the solubility of the gas. And it depicts that by a very simple equation. Here we have solubility, which is going to be in units of molarity. And we have the pressure of the gas, which will be given in units of atmospheres. And ultimately, the K constant here, which is known as the Henry constant, is given in units of molarity per atmosphere. And it's very characteristic of every gas that you may dissolve in water. So for this type of problems, I can give you the partial pressure of the gas along with the Henry constant and have you calculate the solubility of the gas. Or I could give you the solubility of the gas and the Henry constant and have you calculate the partial pressure of the gas. Or alternatively, we can determine the partial pressure of the gas, the solubility of the gas in water, and using those two parameters determine the value of the Henry constant, which is usually how you do this experimentally. Another way to go about it will be to kind of do what we are showing right here with the graph, namely to plot solubility values for the gas at various partial pressures, in which case the slope of this line will equal Henry's constant. So there's different ways to approach this problem. And in this set of lectures, I'm not necessarily going to go into an example of it because this is kind of a very simplistic equation. But the big idea is that as you increase the solubility, you will increase the partial pressure of the gas and vice versa. Greater partial pressure, greater solubility. The thing where it gets kind of tricky is with temperature. The solubility of a gas, which is the solute, you might expect that if you increase the temperature, you're going to get more gas dissolved. But in reality, the opposite happens. If you increase the temperature, the solubility of the gas goes down. And the reason why that happens kind of brings us back to the structure of water, which I presented in the pretty much 2 lectures ago. The idea is that water, creating the hydrogen bonding network that you see here, creates these cages, these empty cages in between, where the nonpolar gas basically parks itself. So the dissolution of the nonpolar gas is not so much that it's interacting with water, but rather it is the gas is occupying the empty space in the hydrogen bonding network cages that water produces. And so, as long as the structure is kept relatively intact, the gas will remain there. But if you start heating up the solution, what's going to happen is that you will provide more energy and more energy and more energy, and eventually you will start providing enough energy, right? Which in this case, 2.5 kilojoules per mole, that's where it is. The hydrogen bond is 8 to 30 kilojoules per mole. So start heating this up enough, and what you're going to end up doing is providing enough energy to break some of those hydrogen bonds. And once the cage is disrupted, the gas has no longer a reason to stick around, and so it just basically evolves and comes out. And it's kind of interesting, but one of the ways by which you can very efficiently degas a solvent is simply by heating it up. If you heat it up under some small vacuum, you will remove all the gas that's present in it. Now, granted, this requires that you do this in a sealed vessel so that you don't continue dissolving gases in the atmosphere into it. But yes, the act of heating up the solid breaks up whatever cage-like compartments it's producing, where basically these nonpolar gases are, finding a place to stay, a place to like hang out for the time being. Disrupt that cage and the gas is gone. All right, so this is the idea with gases. What I'm going to show you on the next section, and by default the next video, is the thermodynamics of salts. So we're going to go back to solutes that may happen to be solids at room temperature by themselves before you even add them to the solvent. But this is basically the idea with gases. Increase the vapor pressure of the gas, increase its solubility. Increase the temperature of the solution, decrease the solubility. So you have those opposite effects. And we'll probably do a few calculations to depict each of those processes. Okay, see you in the next video.